In this lesson, I'd like to look at graphs of motion. I call it part 1 because in this lesson, we will only look at distance or displacement versus time graphs. There are other types of motion graphs that we will get to later on. We have been looking at motion in terms of distance or displacement, speed or velocity, and recently we were introduced to acceleration calculations. Now these are all measurements, or they are calculations from measurements. They are all variables, and they are all related to each other. One way to explore relationships is by using graphs, and that's what this lesson is about. Suppose, for example, that we gathered data on a moving object and we put our data in a data table, something like this. We can now construct a graph from this table. On this particular graph, I let time be the horizontal axis and distance the vertical axis. As you can see, for this particular object, the data are linear. There is a direct relationship or a direct proportionality between the variables. In other words, when one goes up, the other goes up proportionally. The fact that we can see there is a direct relationship is useful, but is there anything else that we can tell about the relationship between these two variables, between distance and time, by using this graph? Well, in math class, your teacher has taught you how to get the slope of a line. Let's try that. Slope is rise over run, so it's the vertical change over the horizontal change. In math class, we would label the two axes x and y, and so the rise would be y-axis, and we would look at the change in y as a numerator. The run would be the x-axis, and we would look at the change in x. For this particular graph, instead of using x and y, we can use the actual terms, distance and time. The vertical or rise axis is distance, and the horizontal run is time. So in other words, in math class, the teacher often labels the axis x and y because they're showing you a generic set of data and trying to point out relationships. But in real life, these would be actually measured values, and so we don't really call them x and y. We call them, in this case, distance and time axes. So the slope would be the change in distance divided by the change in time. To find the slope, we could pick any 2 points that we like. So I drew 2 red dots on the graph. Let's call the lower point number 1 and this upper point number 2. You see the ordered pairs for each of these points, 4, 4, and 5, 5. Now all we have to do is substitute in these values in our equation. So if slope is distance 2 divided by distance 1, that would be 5 meters minus 4 meters. If time is the x in this case, then it would be 5 seconds minus 4 seconds. The result would be 1 meter per second. I hope you realize that I kept up with the units during my calculation, just like I would any other calculation in physics, and I came up with this quantity, 1 meter per second. And that meter per second seems somewhat familiar, doesn't it? Meter per second is one way to measure speed or velocity. In other words, the slope of this distance versus time graph gives me the speed of this object. So that's a pretty neat trick. If I graph distance versus time data, the slope of the line gives me the speed. Or more technically, it gives me the average speed since I'm measuring it over a length of time. So 1 meter per second means that for every second that passes, the object travels a distance of 1 meter. Let's look at a different graph and see if that trick works again. Now first you should note that I changed the rise to displacement. That means we're using a vector quantity this time and paying attention to the direction. So this is a displacement versus time graph. This graph displays a straight line. It shows a linear relationship, but it goes down to the right. The last time we had a graph upwards to the right. So obviously this motion is somehow different. This is an inverse relationship. As time goes up, displacement goes down. Now first I should probably point out that you may not be used to seeing a negative time, but it simply means that we're designating something as the starting point, but you can look and see what happened before that. You would just designate those as negative times. So the slope is the change in distance divided by the change in time. We can pick any 2 points. I'll pick those 2 points right there. The upper one, let me call that number 2, and the lower one I'll call number 1. It really doesn't matter which way you put them as long as you fill in the equation correctly. So the upper point would have an x or time value of -3 and a y of 5. The number 1 point would be a -2 and a 4 on the y-axis or displacement axis. So there's our ordered pairs. And like I said, you just got to be consistent now when you plug that into the equation. So it's going to be 5 meters minus 4 meters. That's going to be along the displacement axis, the y. And then the times are -3 and -2. Now since it's a negative of a negative, that changes into a positive. So in the denominator, I'm going to have -3 plus 2, which is -1. And in the numerator, it's going to be +1. My units are meters and seconds. So my slope is -1 meters per second. Now, what does a velocity of -1 meters per second mean? It does not mean that the object is slowing down. What it means is that it's a velocity, so the negative is indicating a direction. The speed is still 1 meters per second, but it's moving in the opposite direction as whatever we're calling positive. So if the car on the left is designated as having a positive velocity, the car on the right, either one of those, is a negative velocity. In the bottom case, it is going backwards, but it doesn't have to be in order to be called negative. It just has to be going in the opposite direction. So we had a positive slope, gave us 1 meter per second. We had a negative slope, gave us -1 meter per second. What about this graph? What kind of slope does it have? We're going to calculate slope the same way that we did before. We'll designate any 2 points since it's a straight line. And when you get the distances, you'll see that it is, actually I guess I should say displacements. It would be 2 and 2 both times, 2 meters. So the numerator gives us a result of 0. So the denominator can be anything you want. The fact is that's going to give us a 0 slope. What it indicates is that the speed or velocity of this object is 0. It is not changing its position. It's sitting still with respect to our frame of reference. The first 3 examples were simply straight line segments, but here we have a more complicated graph. what kind of motion is represented here. Clearly, the motion of this object changes over time. Between points A and points B, or time 0 and 5 seconds, the object has a direct linear relationship, and in fact, its slope is 1 meter per second, so its velocity is 1 meter per second. Between point B and point C, the object does not change its displacement. It stays at 5 meters. So this would have a velocity of 0. It is not moving over time. Speed equals 0 or velocity equals 0. Between point C and D, the object has an inverse linear relationship. If you calculate the slope, you will get minus 1 meter per second. That means it's headed in the opposite direction as AB. It is not necessarily moving backwards, it's just going in the opposite direction. Now, sometimes when people start seeing graphs like this, they get confused and think that somehow this represents a picture of the trip. But the object did not go over the top of a hill. This is not what the graph represents. Instead, what it's showing you is, if we think of the object as a car, it leaves at some time, goes a certain distance at a certain constant speed, stops for a few seconds, then goes back in the opposite direction at a constant speed. So, what would the total displacement for the entire trip be? Displacement, or change in position, equals final position minus initial position. If you look at D, it is at position 0 meters. If you look at A, it's also at 0 meters. Therefore, the displacement is 0. That does not mean the object didn't move at all. It means that after it moved, it returned to its original starting position. What would the average velocity be for the entire trip? Well, velocity is displacement over time. But seeing as displacement between A and D is 0, it really doesn't matter what the time is, but it would be 13 seconds for the entire trip. That gives a result of 0. So even though the car moved and went somewhere, if you look at the average velocity over the entire trip, because velocity is a vector value and includes direction, and it ended up back where it started, the average velocity would be 0. Sometimes things that you calculate really aren't very useful, but you have to pay attention to what the question asks. Now, the point of this lesson is that a graph can give you information about different parts of a motion event or information about the entire event. You have to be very careful to specify, or if you're reading a problem, to read carefully exactly which portion of the trip you want information about. And it is extremely important to pay attention to the axes. Do they say distance versus time, or displacement versus time, or something else? We will be learning about other graphs later on, which have things like, say, velocity versus time. And the other thing that you have learned is that the slope of a line, a calculation you can make from a graph, can be very useful in telling you something about the way that object has moved. In the case of a distance or displacement versus time graph, the slope is the speed or velocity. I want to point out just one more set of distinctions that you have to be careful about. When we're talking about speed or velocity, it can be a constant speed, it can be an average speed, or it could be an instantaneous speed or velocity. So we have to be very careful about reading what the question is asking us. If it is a constant speed, that means if you compare any 2 points in time, the speed would be the same. So if you see a straight line, then that is a representation of a constant speed if you have a distance or displacement versus time graph. On this particular graph, points A, E, and B would all have a velocity of 1 meter per second. Now, average speed can be calculated over any given time interval. We could do it just, say, for a short segment like A to E or E to B, or we could do it over a longer period of time like A to C or even A to D. In fact, you can calculate it between any 2 points in time, even ones that aren't labeled here. Instantaneous speed means what is the object doing right now, not over some period of time. So technically, it means the interval of time is vanishingly small. It's not even a real thing. So in the case of a constant speed, the instantaneous speed is going to be the same at any given moment. Thank goodness for straight lines. But the speed does not have to be constant. It can change over time. So you might get a graph that looks like this, for example, that has a curve. This displacement versus time graph is showing increasing distances between the displacements over every second. The line segments are getting longer and longer. For this particular graph, the slope at a given point would in fact represent the instantaneous speed. But we can only approximate those slopes with our calculations unless we decide to use calculus. This particular object, since it is having an increasing distance over time, is accelerating. It is speeding up. Now, as I said, you could calculate the slope of this line at a given point. It's called a derivative. If you've had calculus, or if you take calculus one day, I'm sure that you will calculate lots of derivatives. For our purposes, we are going to either just approximate or just not do the math at all with a graph like this. Instead, all I want you to be able to do is recognize that if it is curving upwards, if you have a displacement or distance versus time graph, and it's curving upwards like a bowl, then that means it is going faster every second. It is accelerating. This graph is curving down. It is slowing down, or in everyday language we might say decelerating, but in physics we call this a negative acceleration. But if you look up around, say, the 800 and the 700 and look how long that line segment is, now look down between, say, 12 and 13. So the displacements are getting shorter over time. The time intervals of each of these dots is the same. It's 1 second. So the time's not decreasing. It's the distance between where the object is from one point to the other. This object is slowing down and has a negative acceleration. Notice the shape of the curve. They say a picture is worth 1,000 words. Well, a graph is a type of picture. It is a visual depiction of data, information. And so they are worth a lot. You can tell a lot about the motion of an object by looking at its graph. But it is a set of skills that you have to learn and that you have to practice. Just be careful to read those axes, and that will go a long way to making sure you are interpreting it correctly. That's all for Graphs Part 1.